Hey guys, welcome back to my channel. BGA package is a very popular package type in the semiconductor industry, particularly for advanced integrated circuits such as microcontroller, microprocessor, ASIC, memory chips, and graphic chips. A BGA package may contain a single high-pin count ICs or several ICs of different functions to form a complex system in package, and more recently a much more complex system that is popularly known as chiplet. Okay guys, let's start learning. BGA stands for ball grid array, which is the formation of the I/O terminals or solder balls on the bottom of the package. There are different variations of BGA packages according to its body size, solder ball pitch, package thickness, and solder ball configurations. There are also variations in the packaging interconnect process, which is a choice between Wirebond and flip chip, and also on the processing complexity, such as multi-chip or stack die inside the BGA package. I will discuss details of BGA package variations along with assembly processes in this presentation. Plastic BGA or PBGA is one of the early versions of the BGA package. It is a molded package with a wire bonded device. JEDEC package code for PBGA is MS-034 with package size of 7 by 7 mm up to 55 by 55 mm. The package is a square shape. Package thickness is from 0.6 mm to 2.6 mm with solder ball pitch options of 1.27 mm and 1.5 mm. Some of the advantages of the PBGA package is high interconnect density and lower assembly costs. With wire bonding as the interconnect process, traditional IC bond pad layout is acceptable without the need for additional expensive RDL and bumping processes. Fine pitch bonding capability allows processing of higher pin count ICs. The substrate layers routing is also flexible and easier with the I/O solder pads arranged in an array underneath the package, which is not possible with the leaded QFP package. Here's a quick comparison in package size between the 304 leads quad flat package or QFP versus 304 solder balls BGA package. The 304 leads QFP package has a body size of 40 by 40 mm and a footprint of over 42 by 42 mm with the leads. In comparison, a BGA package with 304 solder balls is only just over 26 by 26 mm in body size and footprint of about 31 by 31 mm. That is about 46% reduction in board space. Fine pitch BGA or FBGA is a package with solder ball pitch of 1 mm or smaller, up to 0.4 mm pitch. With fine pitch solder balls, the package can accommodate very high pin count ICs within a smaller package footprint. And with higher pin count density, the package is quite popular for multi-chip and stack die applications. The package type is fully molded and can be a square or rectangular in shape. Body sizes ranges up to 27 by 27 mm, and thin package profile of under 1 mm is also available. Let's now talk about flip chip BGA. Flip chip significantly increases the number of I/O terminals per unit area and improves package electrical performance, making it very popular for high pin count and high performance ICs. Flip chip BGA, particularly large package sizes, is ideal for workstation processors, high bandwidth system for communication devices, gaming system processors, and graphics, as well as high-end application processors for leading-edge portable devices. But flip chip advantage is not only about space. Advanced ICs and systems with thousands of I/Os use a significant amount of power, and this power is transformed into heat, making the silicon chip so hot that it's more than enough to boil water. With flip chip technology, the die backside is exposed and available to directly attach a heatsink, and that it can also serve as a lid to protect the device. Obviously, heatsink diffuses heat from the device, thus improving the device's overall thermal performance. The variety of flip chip BGA package options allows package selection to be tailored to the specific thermal needs of the end product. High-end performance ICs typically uses lidded format that features a controlled thickness of thermal interface material that directly attach the die backside to a copper heat spreader or lid. This produces lowest thermal resistance between the package and any externally applied thermal solution or heatsink. Also, the lid effectively spreads heat laterally away from the die to the package perimeter and into the motherboard or PCB. Lower wattage products generally utilize bared die or molded package options. With flip chip technology, the solder bumps and core vias provides a lower thermal resistance path from the active side of the die through the substrate, allowing heat dissipation both from the die and package and into the motherboard or PCB. BGA package is about reducing board space and better performance. But this is not possible without having the right substrate material and design. So let's learn about BGA substrate, the industry standard, the materials, and the layers within the substrate. IPC 6010 series is a set of standards for printed boards, both flex and rigid, which includes laminate BGA substrate. I will discuss briefly some of these IPC standards in the next slides. IPC 6011 is the generic performance specification for printed boards. The scope includes general requirements for printed boards and the quality and reliability requirements. This standard also defines the different performance classes for printed boards. As defined in IPC 6011, there are three different classes for printed boards. Class 1 is the general electronics products, which includes consumer products and some computer and computer peripherals suitable for applications where cosmetic imperfections are not important, and major requirement is function of the completed printed board. Class 2 is the dedicated service electronic products, which includes communications equipment, sophisticated business machines, instruments where high performance and extended life is required, and for which uninterrupted service is desired but not critical. Certain cosmetic imperfections are allowed. Class 3 is the high reliability electronic products, which includes the equipment and products where continued performance or performance on demand is critical. Equipment downtime cannot be tolerated and must function when required, such as in life support items or flight control systems. Printed boards in this class are suitable for applications where high levels of assurance are required and service is essential. IPC 6012 covers the qualification and performance requirements for rigid printed boards, which includes most laminate substrate for BGA package. The standard covers different types of printed boards, from single and double-sided, with or without plated through hole, to multi-layer printed boards with plated through hole and with or without vias or micro vias. It also covers printed boards with embedded circuitries and metal core printed boards. Overall, the standard sets 6 different printed board types as shown on this slide. IPC has also defined sectional standards for rigid, flex, multi-chip module, and high-density interconnect printed boards. The standards provide applicable detailed requirements that are important and critical to design, fabrication, and qualification of printed boards. IPC 2226 for HDI contains details about construction and layers requirements applicable for BGA laminate substrate. The image represents the typical layers and construction of a laminate BGA substrate. The middle of the substrate is the core material with copper foil as conductor on both sides. On both sides of the core are built-up layers of prepreg and copper foil or conductive materials that are used for routing signals. Plated through-hole vias are formed to make the connections from top to bottom of the substrate. Buried and blind vias are formed to make connections between prepreg layers. The substrate core provides mechanical strength and stability to the laminate substrate. Depending on chip or system complexity, more layers are necessary to properly route the signal traces. Additional microvias, blind, buried, and stuck are created within each layer of the substrate. The core adds additional thickness to the substrate. In some applications, vertical space is limited, which means thinner package is required. To achieve a thinner package, the use of a coreless substrate is necessary. A coreless substrate makes connection between layers shorter, thus electrical performance is better. It is, however, prone to warpage, which may affect the package reliability. Core and prepreg are both layers within the laminate substrate. But what is the difference or similarity between these layers? The prepreg material is made of fiber or glass weave impregnated with the resin. The resin is hardened but left uncured, while the core is made of layers of prepreg that are pressed, hardened, and heat cured, and finally plated with copper foil on both sides. The heat curing process bonds the layers of prepreg, and the hardened resin cures through cross-linking, which set the core material properties. Let's now discuss the assembly process flow for a BGA package. BGA has many different configurations depending on package size, bump or ball pitch, package thickness, and interconnect process. But assembly process flow is mainly dictated by the type of interconnect process. There are two interconnect processes available for BGA package: Wirebond or flip chip, or both. On this slide, we will talk about the assembly process flow for a wire-bonded BGA package. A wire-bonded BGA uses a standard die wherein the die terminals or bond pods are arranged on the die perimeter. The bond pods are metallized with aluminum suitable for wire bonding process. The assembly process starts with thinning the wafer to the required thickness, which is commonly called as the wafer backweighing process. After backweighing process, the wafer goes to the saw process, which is to cut the wafer into individual chips or die. BGA devices are typically thin and large chip size and with narrow substrate. With this, the wafer is mounted on a UV tape that sufficiently holds the wafer in place during the sawing process. The die attach process is a process of mounting the individual chips or die onto the laminate substrate using adhesive epoxy or tape. The adhesive epoxy is typically heat cured to achieve the adhesion or mechanical strength required to hold the die in place for the next assembly steps and for the lifetime of the device. Once attached to the substrate and epoxy is cured, the device will proceed to the next step, which is the wire bonding process. The bonding process is a delicate process and requires the device, particularly the bond pad, to be very clean. The previous processes wherein the die is exposed to the environment and also to the epoxy outgassing during curing process may introduce contamination to the bond pads, and likewise the leads on the substrate. The common process to clean the bond pads and the leads is the plasma cleaning process. Once plasma cleaned, the device is then ready for wire bonding process. BGA package is widely used for advanced ICs with many input-output pads. Advanced ICs are typically made smaller using new wafer fabrication technologies, and with hundreds of IOs, the bond pads are really small and pitch are tighter. In general, BGA package requires fine pitch bonding process using either gold or copper wire. In addition, smaller chip with a high pin count would result to a long wire span, and thinner package would require a low loop bond process. Overall, BGA wire bonding process requires fine pitch, low loop, and long wire span capabilities. After wire bonding process, the device is now more fragile, with both the die and wires still exposed to environment and also prone to handling damage. So, it is now time for molding process. Once molded, the wire bonded device will be protected and more rugged for handling. However, molding is not just about covering the chip and the die. It must stay intact, solid, and robustly attached to the surface of the die and the substrate. To achieve this, it is critical that the die and substrate surface are free of contamination. The exposure to heat and environment during wire bonding process can lead to some degree of contamination. Similarly, plasma cleaning the wire bond device will clean both the die and substrate surface. After molding process, the next assembly steps are more straightforward. The BGA package is laser marked for required identification, which typically includes a device code, date code, and manufacturer location. Other information are added if needed and if space allows. Next steps are ball attach and singulation. After singulation, the individual package devices are electrically tested. Finally, I'll be discussing the assembly process steps for a flip chip BGA package. The first step is the bumping process, wherein the die bond pads are rerouted and redistributed to match layout appropriate for flip chip configuration. The bump wafer will then go through the backgrain process, where it is thinned to the required thickness, followed by the saw process to cut the wafer into individual bump chips. In some cases, bump dies are transferred to a carrier, such as tape-in reel or waffle pack, which can then be sold and processed in a smaller batch quantity. The steps to transfer bump dies into a carrier is called the pick and place process. After saw and pick and place process, the bump dies are now finally ready for flip chip process. The process is typically done using a high-speed flip chip bonder. Flip chip requires application of solder paste on substrate pads. There are many different types of solder that can be used for flip chip process, and some may or may not require additional flux to achieve good soldering quality. After flip chip, the populated substrate will pass through the reflow oven to complete the soldering process. After reflow, depending on the solder material used, the populated substrate may undergo a cleaning process in preparation for the next step, the underfill process. The underfill process uses epoxy resin, and it fills the gap between the bumps, die, and substrate. Once cured, the underfill provides solid mechanical support to both the die and bumps, preventing cracks on the solder joints and bridging the large gap in thermal expansion of silicon die and laminate substrate. Once underfilled, the package is ready for encapsulation, either by molding process or by using a metal lid that is attached to the die backside. Using metal lid gives better thermal dissipation, as the heat is transferred from the die to the metal lid and finally to an external heatsink. In some cases, there is no metal lid and the heatsink is directly attached to the die backside. The next process steps are ball mount and singulation. And finally, once singulated, the packaged device will go through 100% electrical testing. You can check my other learning videos for detailed topics related to specific processes, such as saw, Wirebond, flip chip, and molding. That concludes another learning video in semiconductor packaging. Feel free to drop a comment, question, or email. To support this channel, please don't forget to like, subscribe, and share this video. Thank you for watching.